Hello students, myself Amrita Dhar, Assistant Professor of Electrical Engineering Department of Greater Kolkata College of Engineering and Management, JIS Group.
In this video I will discuss about design of heating element. This topic is included in module 3 of the subject utilization of electric power. Subject code is EE702. This is the second part of resistance heating. In this video I will discuss about temperature control of resistance furnace and design of heating element. So first, temperature control of resistance furnace. Since voltage of supply and resistance elements are independent parameter and current through element is dependent parameter, there are basically three types of temperature control. First, by varying applied voltage. Secondly, by varying the resistance of the element. And thirdly, by varying the ratio of on and off times of supply. Okay. So first by varying the applied voltage, second varying the resistance, and third varying the ratio of on and off times of the supply. So we can classify temperature control of resistance furnace into three categories. First, by varying voltage across element, second by varying resistance of elements, and third, periodically switching on and off of electrical supply. This is achieved by autotransformer or induction regulator, by series impedance method, and by varying voltage supply. Okay, and this method is achieved by variable number of heating elements and by series parallel or star delta arrangement of elements. Okay, so first, autotransformer or induction regulator. First procedure by for varying the applied voltage is using autotransformer or induction regulator. So first I draw the diagram. Okay, so by providing different taps on the auto transformer or by varying the position of the rotor of an induction regulator, we get variable voltage supply for the furnace. Okay. Next procedure is series impedance. Series impedance. So first I draw the diagram. Okay, so by connecting impedance in the series with the element, we apply reduce voltage to the element and therefore reduce the current, and this method is wasteful and then therefore used only for small furnaces. We connect this impedance with series with the element, but there is a huge amount of voltage drop, so we limit application of this type of method to small furnaces. Next is variable voltage supply. Next is variable voltage supply. So if the furnace is very big and there may be independent generating set for the furnace, we can give variable voltage supply to it. So by these three methods, auto transformer or induction regulator, series impedance, and by variable voltage supply, we can control the voltage, applied voltage across the element. Next, we varying the resistance. So the first procedure is variable number of elements. Variable number of elements. Variable number of elements. So if R be the resistance of one element, R be the resistance of one element, and N be the number of elements working in parallel, working in parallel, then total resistance of the element is R by N. So in this case, heat produced in furnace is equals to V square R by N, or we can write Vn square V square N by R. So I draw a diagram. So as shown in this figure, by putting more and more parallel resistance in the circuit, we can change the temperature, and with this method we get uneven heating unless elements not in use are well distributed. This means this is a complicated wiring. Okay, so next procedure is series parallel or star delta arrangement of elements. Series parallel or star delta arrangement of elements. In case of single phase supply, the heating elements can be put in series for low temperature or in parallel for high temperature. Okay, and by means of series parallel switch, in case of three phase supply, elements can be put in star for low heat, and for high heat it's put in delta by means of star delta switch. So for high heat for three phase we prefer delta, and for low heat in three phase we prefer star, and for single phase line we put element in series and heating element in series, and for high heat for three phase we put this into parallel. Okay, so this is for three phase and this is for single phase. Okay, now next procedure of temperature control of resistance furnace is by varying ratio of on and off time. Okay, so we can say periodically switching on and off the electric supply. Okay, so this method of temperature control is used in case of small ovens. Here the supply to the oven is given through a thermostat switch, which switches on and switches off the supply at particular temperature, and final temperature attained is proportional to the ratio time interval switch remains on by total time interval of the on-off cycle. An advantage of this method is that it is more efficient than series impedance method. Okay, so this is all about temperature control of resistance furnace. Next is design of heating element. Design of heating element. Now in the design of heating element for electric furnace, the choice of the element alloy is made on the basis of temperature of the furnace, the wattage P of the furnace, voltage of supply V, and absolute temperature of charge being known, and we require to find out the diameter and length of the wire and diameter and length of the coil. So P is equals to V square by R. We all know this formula, and R is equals to so we can write R is equals to V square by P. Now R is equals to rho L by A, and A is the area, so we can write pi by 4 d square. So from this capital L pi d square, sorry, this is capital L, and capital L is equals to pi v square by 4 p into rho, and this is d square. Okay, from this and this we get this expression. So in the high temperature furnace, whatever heat is produced in the resistance of the element has to be radiated to the charge according to Stephen's law. So what is Stephen's law? H is equals to 5.72 ke T1 by 100 to the power 4, T2 by 100 to the power 4 into watt per square meter, where T1 and T2 are the absolute temperature in Kelvin of hot and cold bodies respectively. Temperature of hot and cold bodies respectively. E is the emissivity, and its value is 1 for black body and 0.9 for heating elements. Okay, and 0.1, 0.15, sorry, and 0.1, 0.15, 0.25, 0.65 for polished aluminium, copper, cast iron and black iron plate. Okay, and K is the radiating efficiency. And its value depends upon the disposition of heating element, and its value is 1 for single element and maybe go down as 0.5 for many element. Okay, for many element, and both E and K are dimensionless. So power radiated is equals to P equals to H by dl. Okay, and this is equal to dl equals to P by pi H, and substituting the value of H and substituting the value of H, and we get the value of D and L. Okay, so now we solve a problem. A 20 kilowatt single phase 220 volt resistance oven employs a circular nichrome ware for its heating element, and if ware temperature is not to exceed 1170 degrees centigrade and temperature of charge is to be 500 degrees centigrade, calculate the diameter and the length of the ware. Where K is equals to 0.57, E is equals to 0.95, rho is equals to 1.09 micro-ohm meter. What would be the temperature of the element when charge is cold? Okay. So R is equals to V square by P. So V is 220 square by 20 into 1000, 2.42 ohm. And the formula of R is rho L by A. R is 2.42. The given value of rho is 1.09 and L by pi by 4 d square. So L by 4 is equals to 174,000. So we calculate, this is L by d square. Okay, now we calculate the value of H. H is equals to 5.72 into 0.57 the value of K, 0.95 value of E. 273 plus 1170 by 100, all are given. 273 plus 500 whole to the power 4. So by solving, this is equals to 12 into 10 to the power 4 watt per square meter. Okay. Now the temperature is given in degrees, so we convert it to Kelvin. So we add 273 with the value of temperature expressed in degree. Okay. Now P is equals to H pi dl. Now what is the value of P? P is given 20 kilowatt, so we can write 20,000 watt, and the value of H is 12 into 10 to the power 4 and pi dl. So from this we can write the value of d square L square is equals to 0.053. Just by solving we get this, and by multiplying L by d square, which is equal to 174,000, and this equation we get the value of L is 70 meter and d is 0.312 centimeter, and taking the outside diameter of the coil as 5 times or mean diameter or coil as 5 times the diameter of the wire, we get diameter of the coil is equals to 5 into 0.312, which is equals to 1.6 centimeter, and number of turn per centimeter length of the coil is 1 by 0.312. Number of turn per centimeter length of coil is 1 by 0.312, and length of wire per centimeter length of coil is pi into 1.6 into 1 by 0.312 is equals to 5 pi centimeter, and length of coil is equal to 1700 by pi into 5, which is equal to 108 centimeter. Since the dimension of element and power of furnace remains same, the heat production rate remains same, and the effect of reduction of charge temperature will increase the heat radiation rate, and this will therefore reduce the final temperature reached by the element. So we can write 12 into 10 to the power 4 is equal to 5.72 into 0.57 into 0.95. T1 by 100 whole to the power 4 minus 273. T2 is given 20 degrees centigrade whole to the power 4, which is equals to T1 is equals to 1403 degree Kelvin. So T1 is equals to 1403 minus 273 is equal to 1130 degree. Okay, this is the answer.
That's all from today's class. If you have any problem, please contact with me. My contact details is given on the first slide. Thank you.